what we have done. We started with the force and stress, which force is defined by push or pull. The stress over area, force over area is the stress. We talked about the tensile stress. We also spoke about cross-sectional properties, where we discussed the neutral axis, the moment of inertia, the radius of gyration, resistance, and we know that these are cross-sectional properties that can be found in the Red Book. We also spoke about the tensile resistance, where I told you about the yield strength, the tensile resistance, and the resistance factor. And also, I spoke about the safety of factor of steel, which is 1.15. I went and spoke to you about the limit state design philosophy, which tells us that the resistance must be greater than the loading, and the load must be amplified, and the resistance factor reduced. That's a summary of limit state design philosophy. And I also spoke to you about the structural member types, which we have tension, compression member, fractional member, which are sometimes called beams, and we spoke about the beams. On the beams, I easily told you that there's a fully laterally supported beam and a laterally unsupported beam, which can also bend out of plane. We also went straight to beam column because that was the purpose of the day, where we discussed that the beam column is actually a combination of a beam and a column. Applied forces creates major or forces in the minor or the major axis. We went on and spoke about the beam column design principles, where we realized that major and minor axes are important as well. Then we discussed that the major axis has a greater moment of inertia, meaning, and we also discussed that minor axis has smaller moment of inertia, meaning it's weaker, and the other one is harder to bend. We also spoke about the beam typically placed along the major axis, and if it fails, it will fail by both lateral torsional buckling. And we also spoke about the biaxial bending, where there's moments applied by both major and the minor axes. And we also spoke about require of two sets of calculations, which is mx and the mi. And we also spoke about the total stresses on the beam column, which is axial stress, bending stress in the x and in the y direction. We also spoke about the beam column connection. If we have a fixed connection, transfer moment from the beam to the column, and we might have the double curvature. The column experience both the axial loading and the bending. We derived the interaction equation for beam columns from the normal stresses and the bending stresses, and we find that it's Cu over Cr plus Mu over Mrx plus Mu over Mr1. And then we went on and applied the Cu and Mu are the applied load, axial, and the moment. Cr and Mr are respective resistance. And we also spoke about the second order effects which affect the Mr and the Mr resistance. We also talked about axial force on bending members generate additional moments and accounted by amplification factor U1 or omega 1. And we also spoke about the code factors, which includes 0.85 to accounts for residual strength and the beta. We went on discussing the failure modes of beam column, which is cross-sectional member strength and overall member strength, and the which is the first one, which is a cross-sectional member strength, the overall member strength, and the lateral torsional buckling. And we went on and is talking about how you design the beam column. The first thing that we do, we need to check the local buckling. We're doing so by firstly classify the flange and the web using the width to thickness ratio and limiting values from the code, and the overall member determined by the weaker component or the axis. The overall member strength also we check the slenderness ratio lambda, CR and MRX consider class 1 and class 2, and the lateral torsional buckling, which requires calculation of critical moment. Check the structures shear modulus and torsional resistance. A minor axis failure is lateral torsional buckling, and the critical stress calculations must be calculated so that you can determine your Euler buckling strength by the weaker axis, and then you use that minimum Fe to determine buckling strength, and then you recalculate Cr based on the maximum slenderness ratio, and therefore you will be done designing the beam column.